All right, so hi, my name is Ethan. I am an educator at the Cheehaw Park and Zoo, the Flint River Aquarium, and the Thronotisia Heritage Center here in Albany, Georgia. And today I'm going to talk to you about space, more specifically about our solar system. Uh, so we are going to switch over here to a PowerPoint. Um, and I entitled it Spacing Out. It's an overview of our solar system. So a couple of the goals that I have for this lesson is to gain a better understanding of the celestial bodies within our solar system. So the planets, um, a couple other notable things that are around. Um, Learn about orbital mechanics and a little bit about how planets tend to move. Um, Learn about the history of our understanding of the solar system. So how our knowledge of the night sky and the planets has shaped history and how history has shaped it. To understand the challenges we still face when it comes to our understanding of the solar system, because we are pretty far from having an expertise on the solar system. There are still huge aspects of our solar system that we barely understand. Um, and Also to learn about what the future holds for our understanding of the solar system. So to start, I'm going to talk about the history of astronomy and how we have been observing our solar system. Um, and we're going to go all the way back to the dawn of man. Um, Pretty much as far back as we have archaeological evidence of us observing the stars, we have been observing the planets. So Mercury, Venus, Mars, Jupiter, and Saturn have all been charted in the night sky for literally tens of thousands of years. Mention of them has existed since mankind began charting stars. As I explained, we actually have like pieces of old bone where the stars are marked, the planets are. Um, the earliest known proper star chart that accurately describes their movements is from ancient Egypt from the year 1534 BC. It suggests that their movements were well known before this, though, and most likely the Egyptians got their data from the ancient Babylonians in central Persia. The Babylonians were pretty big on stars. We got our ideas of astrology, like the astrological signs, originally come from ancient Babylon and possibly actually come from a civilization that came about before Babylon that we don't have much data on, found in this sort of Indo-European area that is Persia. So long story short, we've been looking at space for forever. Just as long as we've been around, we've been looking at the stars, and more specifically looking at the planets as well, because we were able to distinguish between the planets and the stars. Even back then, we knew that they moved differently from the rest of the night sky. Um, so, uh, yeah. Um, so now we're going to get into just a little bit more in detail about uh, early sort of discoveries of antiquity before really science had become well a science. There were a lot of observations made, but not a lot of hard mathematics or things like that. But our best knowledge of our solar system actually comes from ancient China around the second millennium BC, so like 4,000 years ago. Chinese astronomers were able to accurately measure that it took Jupiter 12 years to orbit around the sun. They did that by marking where it was in the night sky a few different times and using a bunch of calculations. It also suggested that they knew that the Earth was round, that the sun was the center of our solar system, and they knew a lot of stuff by then. So this sort of fact that we know that they had a 12-year that we knew that they knew Jupiter's orbit also tells us, in addition, that there was a lot of information that they knew as well that we just don't have access to anymore. They also knew the times of the spring equinox, and they also were able to, we know that they were at least observing solar eclipses because they had described them in some of their earlier works. So 4,000 years ago, the ancient Chinese astronomers they had a very deep fundamental knowledge of how things of what the planetary bodies were doing, um, all the way down to the fact that they were able to calculate Jupiter's orbit, and they were right. Jupiter does have a 12-year orbit, so they were pretty much exactly correct. Now, if we get a little bit more recent, in the 7th century BC, um, Egyptian astronomers were able to accurately predict when a solar eclipse would occur. So they were able to predict that sort of thing as well. Also around that time, Chinese astronomers recorded what we believe was Halley's Comet, or Halley's Comet, or however you want to pronounce it. And in 450 BC, a predecessor to Aristotle, Anaxagoras showed that he was able to prove that the moon reflected the sun's light. And then only 100 years later, Aristotle argued for a spherical Earth after observing lunar eclipses, which is kind of an interesting thing. He looked at lunar eclipses and he said, "Hey, that's our reflection, and it's hitting the moon and making a round shape. Therefore, we must be round," which is a very smart observation. Um, so whenever you start to get a little bit closer to the Common Era, um, you get things like in 280 BC, we had several proposals for heliocentric models just around the world. People in India were proposing it. People in China were starting to write about how the sun was at the center of, well, the universe to them, but the solar system. Um, all of these different heliocentric models were being proposed. And a guy named Hipparchus calculated the distance between the Earth and the moon. He was able to calculate the distance between the Earth and the moon in 280 BC, which is pretty wild to me. Um, and he did that using, I believe, shadows from the full moon. He calculated using a shadow how far away the moon had to have been. Um, so it was very simple math that got him to the number that he had, in a very similar vein to how we were able to calculate the Earth's circumference by just looking at two shadows in two different spots at the same time and sort of calculating the difference. He was able to calculate based off of the angle that it was hitting an object and the shadow being cast off of it, how far away the moon had to have been, which is pretty crazy to me. He also determined when the equinoxes were, so he gave us that as well. In 87 BC, we have the Antikythera mechanism, or the Antikythera mechanism. I'm not sure how to pronounce it, but it's the oldest computer. It's considered the oldest computer. It was a mechanical device that was able to predict celestial positions. So you could say, where is Jupiter going to be in 200 years on this date? And you were able to just punch that in and sort of turn some mechanical keys, and it would spit out the answer, which is what made it a computer. It was able to calculate things for us, so we didn't have to do the calculations on our own. But the oldest example of a computer actually predicted positions of the planets. In 28 BC, we have our first written description of a sunspot, which, for those of you who don't know, a sunspot is this sort of slightly darker area on the sun. It's where it's ejecting plasma into space. That's what a sunspot is. And they're not observable to the naked eye, obviously, because you'll burn your eye out, but they are observable if you have special devices that can do it. So like if you're looking through a lens or an inverted reflection, you can see sunspots. The Catholic Church actually used to observe sunspots pretty regularly during the Renaissance. But a long time before the Renaissance, nearly uh, over 1.5 millennia before the Renaissance, the Chinese were observing sunspots. And then in 150, the year 150 in the Common Era, Ptolemy codified all of the knowledge that he knew of the solar system. And whenever he did it, he made a couple very important decisions that had ramifications for the future. So he was documenting all of these things that we knew, the distance that the moon is away from us, equinoxes, seasons, all of that fun stuff that he knew about through interacting with other people. And he codified it all. And then he said that the Earth was the center of the universe and that everything revolved around the Earth. And that had serious consequences because everybody that came after Ptolemy that had access to his work used his work and analyzed his work, which means that they also believed that the Earth was or that the solar system was geocentric, that it orbited around the Earth. So just this one man's decision to double down on a debated topic made it so that for several hundred years, we believed that the Earth was the center of the universe. So to sort of summarize this very early part of astronomy, we were using some simple observation and some very basic math to calculate things. But even just with that basic math, we were able to calculate orbits of planets. So like we knew how long Jupiter took to orbit. Our own planet's size, we were able to calculate. We knew about seasons and when the seasons changed. And we were even making observations of celestial events like eclipses and understanding what caused them and when they would occur. Things that we still were sort of not there yet on are things like heliocentrism. Towards the end of the ancient era, we abandoned any ideas of heliocentrism, of the idea that the sun is the center, and started really going towards Earth being the center. And a large part of that, I believe, had to do with the rise in Abrahamic religion, believe it or not. Things like Judaism and Christianity, and then later Islam tended to skew towards this idea that Earth was the center. It was the most important part. And I mean, from our perspective, the sun rises. It's not stationary. We're stationary, you know? But they sort of doubled down on that idea of geocentrism. So whereas the ancient era was a lot of observations and simple calculations, we start to see some slightly more complex calculations and some fancier ways of observing space during the Middle Ages. So the Middle Ages, not a lot was happening in Europe that was in the way of scientific advancement, but in India and in Islamic countries, like in the Middle East, there was a golden age of science and mathematics. So a lot of the advancements in science, in astronomy that occurred in the Middle Ages occurred in India and in the Middle East. So I might have a hard time pronouncing some of these names, but in the year 500, around the year 500, there was a man named Aryabhata who calculated when solar and lunar eclipses would occur, where they would occur, and the Earth's rotation around the sun. So he was able to tell us definitively how long it took for the Earth to rotate around the sun, which we already had a fairly decent idea about, but it wasn't the best. The thing that we were really good at this point was being able to tell how long a day was, because the ancient Babylonians and the Mesopotamians had actually figured out how long it took for us to make a complete rotation. But we still were figuring out our orbit. A man named Brahmagupta in the 1620s did a whole bunch of stuff. This guy was kind of a rock star of the Indian Golden Ages. He described gravity. which is our first written description of the force of gravity. He calculated for orbits of other planets, including their rising and setting in the night sky, how they moved across the night sky, and when they would meet with each other. So he really, really nailed how planets moved in our night sky. And he also described why they moved a little bit. And this is one of the first examples of us analyzing why, as opposed to just observing something. He didn't use the term gravity, but he described what was essentially gravity. He believed that objects pulled on each other, and that's what was making things move around. In the 9th century, you get a man named Jafar Muhammad ibn Musa ibn Shakir, and I might have mispronounced that. I'm not an expert. He hypothesized gravity as well, and that all celestial bodies have to follow the same rules of physics that we have to follow on Earth, which sounds really obvious to us, but it was a very important step, understanding that any object in space had to follow the same rules as here on Earth. So then in the year 1031, we had another man, and I'm not even going to try to pronounce his name this time, but it's right here. And he calculated the distance between the Earth and the Sun with a very, very good degree of accuracy. He was very accurate whenever he did it. Oops. And we also got Bhaskara II in 1150, calculating the latitudes and longitudes of each planet, their orbits, their seasons, pretty much everything about the planets that's observable, he was calculating. In the 1150s, Ptolemy's works were translated into Latin and adopted by the Catholic Church, which went a long way towards setting up what would soon be the Renaissance. In 1200, this man, who I'm also not even going to attempt to pronounce, proposed he proposed string theory, essentially, a much more simplified version of modern day string theory, which is the idea that there are essentially an infinite number of universes for every possibility of things that could occur. He suggested that there were tons of planets out there that could be just like Earth and could have people on it and could do all of this stuff, because if you look at the observable universe, it's so massive that it would be a statistical improbability for us to just be alone and just exist on our own. So this man in the year 1200 was making some very, very bold claims that resonate even today. And then in 1514, we finally see in the Western world the heliocentric model get adopted after Copernicus proposed it. He had observed other Islamic heliocentric models that were proposed by Islamic scientists, and he finally drove the nail home. He drove it home in the Western world. So in 1570, we also got a man named Tycho Brahe. He founded the first observatory, and he also proved that comets are celestial objects, not just atmospheric weird happenings. So to summarize the Middle Ages, we see a couple things get a little bit more advanced. We start to see people questioning why things happen instead of just observing that they do, which is where we get some ideas that were very, very, very ahead of their time, like gravity and orbital mechanics being described. We still don't understand the causes of those things yet here in the Middle Ages, but we're starting to get there. Heliocentrism slowly starts to see its way back into the limelight. It's kind of crazy how one man with a very popular work of science who could get one thing wrong there, it just sticks for so long. But then the solar system begins to be clearly defined, and an understanding of seasons and planetary motions are very well documented. But what we still don't know yet are things like the fundamental forces driving the celestial motion, and anything about the planets specifically. Like we know that they're there and we know that they're moving around, but we don't really know much about them. So now you get into some things like the Renaissance, and moving forward in after the Renaissance comes the Enlightenment era. And so in 1609, Kepler, Johannes Kepler, described the laws of planetary motion. So he got us the next step after the heliocentric model was describing orbits as ellipticals and showing that planets follow an elliptical motion. Galileo observed Saturn's moons and rings with his new telescope. Telescopes existed before this, of course, but his was a lot fancier. It used refractive lenses to magnify things. He also observed Venus and how it seemed to change over a season. In 1655, a man named Giovanni Domenico Cassini, which, if that name sounds familiar, it's because there was a satellite that was sent to Jupiter here a little while ago named after him, but he observed Jupiter's big red spot, and he also determined the speeds of rotation for all the planets and the moons, some of the moons of Jupiter. So like, for instance, he calculated that Jupiter sped really quickly around, whereas other planets like, say, Venus, barely rotated at all. We also see the standardization of celestial objects' distances. So we all start agreeing on how far away things are, and we come up with what's known as the astronomical unit at this time. And the astronomical unit is a very important thing. It is the average distance between the Earth and the Sun. That's an astronomical unit. So at any given time, the Earth is about 1 astronomical unit. Now it fluctuates ever so slightly because the Earth does have a slightly elongated elliptical orbit. Sometimes it's a little bit further away than other times, but it is usually about 1 astronomical unit. And so what we do is we calculate everything in our solar system in terms of astronomical units. In 1675, we also get a man named Ole Romer, who estimated the speed of light after watching Jupiter's moons, which is kind of crazy. He was able to estimate the speed of light to a pretty good degree of accuracy after observing Jupiter's moons and how light played off of them in his telescopes. All right, so we're starting to get into modern day here. So the last few hundred years, we get the man, the myth, the legend, Edmund Halley, who predicted Halley's Comet and named it after himself. He also would later track solar eclipse shadows, so he could more accurately measure the distance from the sun and the motion of our stars. In 1729, a man named James Bradley calculated and observed how stars move in relation to the Earth as it moves around the sun, which seems like a lot of math, right? So he's figuring out where the stars will be on any given day by doing calculations. In 1755, you get a man named Immanuel Kant, who proposes the nebular theory of how the solar system is formed. So he was the first guy to say, hey, maybe it all came from the sun. Our solar system all must have come from one place originally, and it sort of collapsed into what we have today. And then in 1787, the same year that the Constitution of the United States of America was ratified, William Herschel discovered Uranus, or sometimes called Uranus, but I call it Uranus because I work with children. This was the first time that a planetary body was discovered that isn't visible to the naked eye. So you can't see Uranus in the night sky. You have to use a telescope to be able to see it. And it was found in 1787. So the 17th and 18th centuries, the math became quote unquote elegant. The mechanics started to fit together a little bit better. And the idea that if physics exist on Earth, they have to exist everywhere became sort of the norm. So we were able to calculate things in other places using the exact same math that we use here. We didn't have to come up with a new equation for anything. So it led to a lot of advancements. We used the scientific method for the first time, really, as we applied it to astronomy. And we also had better telescopes, which led to better observations of our night sky. So now comes the 19th century. You get Ceres, identified right at the beginning of the 19th century in 1801. Ceres is a round asteroid. It is a dwarf planet. It's large enough to have become round on the outside, but it exists within our asteroid belt. You also get people in as early as 1821 describing irregularities in Uranus's orbit, which suggests that there is another planet somewhere nearby, altering its orbit. Pierre Laplace, in 1825, completed his works on gravity and tidal motion. So he was the first guy to really describe why tides work the way that they do. And in 1843, John Adams, not that John Adams, a different John Adams, he was a British mathematician, predicted the existence of Neptune based off of all of these observations people were having on Uranus's orbit. And in 1846, only 3 years later, a man named Johann Galle discovered Neptune, finally. So we had actually kind of known Neptune existed, and in as early as 1843, we were able to tell exactly where it was before we actually found it, which I think is a very interesting fact. The math had already proven the observation before the observation was made, which is good science. That's a sign that they were doing things right. There's also in 1849 a man named Edward Roche, who described tidal forces of destruction and how planets can hold together by gravity alone. So this man brought us a step closer to our understanding of how the planets formed in the first place by describing what's known today as Roche limits, which is whenever two celestial bodies get so close that they begin to tear each other up. So like, for instance, if the moon was closer to the Earth's gravitational force would suck the moon in, and it would no longer be able to rotate and orbit Earth. It would just get ripped apart. That's true with the sun as well. And that piece of information helped us to better understand how the planets formed by quite literally ripping each other apart until there were only a few left. In 1862, a Catholic priest, Father Angelo Secchi, determines officially that the sun is a star after observing a bunch of different stars and noting that the sun had the same composition as them. So he officially laid it to rest, guys. The sun is a star. I just think that that's a really fun thing because it means that officially the sun wasn't considered a star until 1862. The Civil War had already started before we definitively said that the sun was a star. In 1866, Giovanni Schiaparelli determined that meteor showers happen when the Earth passes through debris fields left by comets, which also means that we were able to predict when meteor showers occur, which is why we're able to do that nowadays. We're able to say, hey, at this time in this year, a meteor shower will hit because we're passing through a comet field. Now we're starting to move into the 20th century, and this is where things start to get a little bit more complex. So up until this point, we've been doing a lot of observation from the ground. We can look, we can do some calculations, we can look with a big telescope, we can do all of that fun stuff. And we had all of these pages upon pages of models of how orbital mechanics worked. But we had different models when observing from Earth. We had a different model for observing here versus here. We had all kinds of different models for observing these things until Einstein showed up and said, no, no, no. Science should be elegant. If you can do it in one place, you should be able to do it everywhere. And he proposed a bunch of things, including his theory of general relativity, which says that no matter which way you frame it, the physics has to be the same, which let me try to explain that one a little bit better here. Basically, what he said was whether or not you are standing on Earth observing Mars move relative to the Earth, or you are standing on Mercury observing Mars relative to Mercury, it's going to be the same math either way. Or if you're standing on Mars, trying to determine how Mars is moving compared to the Earth, it's all going to be the same exact math. And so that's what the general theory of relativity does, is it states that everything exists in what's known as space-time, which is sort of this like fabric of reality kind of situation, and that gravity warps space-time. So almost like if you have like a set of nylon like stretched out and you set a big weight in the middle, it will make the nylon stretch. Well, gravity stretches space-time in just the same way. It's just instead of like in a 2D space stretching it out, it's stretching it everywhere all at once, like an infinite nylon. And that because it stretches it, other things will move in and hit it. Basically, he rethought of the idea of gravity. Instead of it being a force, it's a reaction. And without going into too much more detail, basically, a man named Arthur Stanley Eddington in 1919 proved his theory correct, because if gravity does in fact warp space-time, that means that technically, if you have the sun, which is this massive ball of gravity, right? It's got a lot of gravitational force. That's why all the planets are rotating around it. Then technically, because even light gets warped by space-time, you should be able to see a star that's behind the sun, on the outskirts of the sun, because it's warping space-time. But the only way that you can see the sun is you can observe that sort of thing is through a solar eclipse. So what Arthur Stanley Eddington did was he ran around chasing solar eclipses around the world and observing the outskirts of the sun during the solar eclipses, and he was able to see stars that mathematically should be behind the sun at that point. And that's how he proved Einstein's theory of general relativity, by proving that gravity warps space-time, which is wild. That's a crazy thing to do, but that's how he did it. In 1930, a man named Clyde Tombaugh, or Tombaugh, or Tombaugh, however you want to pronounce it, discovered Pluto. And also in 1930, a man named Seth Nicholson was able to record the surface temperature of the moon from Earth, which opened the door to all sorts of calculations of the planets from Earth. In 1935, a balloon called the Explorer 2 got 22,000 meters above the ground, and the occupants could see the curvature of the Earth clearly. In 1944, a man named Gerard Cooper discovers the moon Titan has a significant atmosphere. Now, Titan is one of Saturn's moons, and he discovered that it has an atmosphere around it. And then in 1946, the American V2, which was a German rocket, but it was adapted by the Americans, launched up with a camera and took the first image of Earth from space, which I have right here. This was the very first image taken from space. So that marked a very important step in our understanding of the universe and the solar system, because now suddenly we're able to leave the atmosphere. We're able to look at space from space. So we get into the Cold War, and at the start of the Cold War, the Russians and the Americans were in a sort of technological arms race to try to get to the moon. But before we could get to the moon, there were a bunch of steps that needed to be done. So there's a huge chunk of space observation that occurs here. So let me just run through the gamut here. We got our first photos of planet Earth from space. We took photos of the dark side of the moon. We got close-up photos of Venus and Mars. We landed on the moon with a rover. We got atmospheric data of Venus, and turns out it's super toxic. We got the first manned orbit of the moon. We got our first landing on the moon. We got some data of Venus's surface, um, and also some topographic info of Mars, all in the span of about, a decade and a half. So it's kind of crazy. We did a whole bunch of research on our near space. Um, we also were able to identify coronal holes, which are what these are. These sort of blackish spots where the sun isn't as bright in the sun, and they sort of open and close over time. And we still don't fully understand them. We just are able to observe them. We had a flyby of Jupiter, and we landed a probe on Venus and had it transmit data. And it turns out Venus is super hot and also incredibly pressurized. It's about 90 times the pressure of Earth. So we learned that Venus was way less hospitable than we were hoping. All right, so after the mid 70s, things don't necessarily slow down, but we get a more long view, a more long-term focus of studying. We've explored the immediate surroundings a lot here, so we start to look at further things. So in 1977, we discovered that Uranus has wings, or Uranus has wings. Rings, not wings, goodness. The Pioneer 11 flew by Saturn and took some beautiful photos of Saturn. The Voyager 1 flew by Jupiter and spotted volcanoes on Io, one of its moons. The Voyager 2 discovered evidence of an ocean under Europa, which is pretty cool. It saw geysers spouting out. The Hubble telescope gets launched. Voyager 1 in 1990 takes its pale blue dot photo. That's a photo that it took whenever it was out by, I think Saturn. It turned around and took a photo of Earth, and it was just a tiny little blue dot. And we also, in 1995, discovered our first exoplanetary solar system, which was 51 Pegasi. It was a Jupiter-like planet that orbited around the star Pegasi 51 once every 4 days. So it's what's called a hot Jupiter, because it turns out they're somewhat common after discovering more of them, but we still have no idea how they formed. And then in the last 20 or so years, we discovered a big rock called Sedna, which had a 12,000-year orbit. We launched a spacecraft to orbit Saturn. We discovered Eris, a dwarf planet bigger than Pluto, out beyond Neptune. We reclassified the planets in 2006, so we declared things like Pluto and Eris and Ceres dwarf planets instead of just calling it a regular planet. We found other dwarf planets like Makemake and Haumea. The Messenger spacecraft completed its first full map of Mercury. It took us until 2013 to actually get a good map of Mercury. In 2015, the New Horizons mission got our first detailed images of Pluto as it flew by. We found our first interstellar object in 2017, as in something that came from beyond our solar system. It's Oumuamua. Oumuamua. And just about a month ago, we landed a helicopter on Mars. So we're moving pretty fast here. It's just a lot of it is a lot. It's more of a build. We're getting better and smarter about how we go about things. So in the future, we'll start to, I imagine, these are predictions. We will be looking more at colonization efforts in our near systems like the moon and Mars. We'll be looking to collect geological samples of other planets. Atmospheric signatures of life on Venus. Last year, we found indicators of life on Venus. Not that we actually found any life on Venus, but it's still very fascinating that we were able to find those indicators. These little microscopic particles in the air that indicate to us that there may be life in the atmosphere of Venus, because we found the same indicators in the atmosphere of Earth in places where there is microscopic organisms floating around on Earth. And also, we've sent several probes out to asteroids, and they should be returning in the near future. So You might have noticed that we did very little exploring of the outer solar system, and that's because it takes a very long time to do that. Um, there's all kinds of challenges to exploring the outer planets, chief among them being that it takes years and years and years for us to get out there. Um, so that's another thing that we will hopefully be doing in the future. So things that we still don't know. We don't really know much about Jupiter and Saturn's moons, and a lot of them have indicators for life, but we just haven't been able to follow up on them. We know almost nothing about Uranus and Neptune, like very little, aside from what we can observe. In fact, Uranus and Neptune have both only ever had one probe, and it was the Voyager. Voyager 1 flew past them. Otherwise, we have almost nothing. We don't really understand how the planets formed yet. We have a lot of theories, and we have a general understanding of it, but there are some things where there are just big gaps missing from our understanding of it. There also potentially could be other planets past Neptune and things like that. We were able to detect planets like Neptune because of their gravitational effect, and there's a lot of things out beyond Neptune that have strong gravitational pulls and do weird things to the orbits of things like Neptune and Pluto and other stuff that we just haven't been able to identify yet. So let's talk a bit about our formation of the solar system before I really get into the weeds about the planets. So it formed about 4.6 billion years ago. And it was formed by what we believe essentially just a lot of dust collected and collected and collected, a lot of hydrogen and a few other elements, until that cloud became so dense that it just collapsed in on itself into a big disk and started swirling and swirling and swirling and spinning and ejecting all kinds of stuff out. And the pressure in the center grew and grew and grew until the hydrogen started combining to form helium, which is what the sun does. It condensed into the sun itself. And I always remember the They Might Be Giants song, What is the Sun? Where it opens with the sun is a mass of incandescent gas. It's great. It's a huge, huge ball of hydrogen that combines into helium. There are other things in the sun too, like there's aluminum and nickel and cobalt and things, but they're all so hot that they are literally a gas. And the particles around the sun began to clump together and formed things like planets. And so all of these things just eventually clumped and maybe ejected and broke apart, came together and broke apart until enough of them were big enough that they started just collecting instead of breaking apart. So the order and location of these planets actually follow a pretty decent pattern. Nearer to the sun, you get rockier planets because all of the lighter gases and things were burned away by the heat of the sun. And then after you get to a certain point, you start to get gases, gas giants like Jupiter, which formed because the sun wasn't able to eject all of that gas. So it just collected a lot of gas. In fact, Jupiter might have collected gas from the rocky planets whenever the gas was getting ejected by the heat of the sun and the formation of it all, which might explain why Jupiter is so big. But we have some issues with this, namely that we don't really understand how something like the hot Jupiter at 51 Pegasi, which only has an orbit of 4 days, it's super close to the sun, but it's roughly half the size of Jupiter and it's a gas giant. Well, if our idea is that rocky planets formed because gas giants can't form that close, then how did 51 Pegasi get there? There are a lot of explanations. One is that our idea could be wrong about how gas giants form, and another one is 51 Pegasi b, which is the name of the planet, could have moved closer somehow. There's all kinds of stuff we don't understand, but just the fact that we don't understand it is pretty good because it means that we have room to grow. And then a lot of these planets, if they were large enough, gathered moons. Usually they're either captured, so like asteroids and other bodies floating by get captured and enter orbit, or they get formed through explosive impacts and ejections of material, which is actually how our moon was formed. The Earth got hit at some point, and a huge chunk of it got sent off into space, and then it all kind of collected into the moon, or some combination of the two. So now we're going to talk about the planets themselves, and I'm just going to run through real quick a little bit about each planet. So Mercury is the closest planet to the sun. It's only slightly larger than the moon, and actually it looks a lot like the moon. If I told you that was the moon, you probably wouldn't dispute it, right? It rotates very slowly. So 1 day is about 59 Earth days, and 1 day-night cycle takes 176 Earth days. Because it's so close to the sun, it just stays daytime and stays nighttime for much longer because it's rotating along with the sun. It has an 88-day year, so once every 88 days, it makes its way around. And its temperature ranges from 430 degrees Celsius to negative 180 degrees Celsius. And it is about 0.4 astronomical units. So it is about 4/10 of the way between the sun and the Earth. And it takes about 2.84 minutes for light to reach it. Then you get Venus, which is similar in size to Earth, but has an extremely toxic atmosphere made out of sulfuric acid and carbon dioxide. It is about 90 times the pressure of the Earth at the surface because of all of that atmosphere. And it also spins in retrograde. It's very slowly spins the opposite direction of the Earth. So the sun actually rises in the west and sets in the east. 1 Venus day is 243 Earth days, but 1 Venus year is only 225. So it actually rotates around the sun faster than it comes to a complete rotation in a day. It takes about 6 minutes for light to reach it from the sun, and it is about 7/10 of the way between the Earth and the sun. Now we get the Earth, which is the only confirmed life in the solar system. Humans have been living in orbit since November 2nd, 2000, continuously, so about 21 years now. Just about almost 21 years, like 20 and a half years. We actually have had at least one person off of our planet at any given time, which is kind of an interesting thought. Not every human lives on Earth anymore. And there has never been a time since November 2nd, 2000, where every human is on Earth at the same time. It has a very nitrogen-rich atmosphere. It has about a 20 to 25% oxygen content. The 70% is nitrogen, and then the rest is other things like carbon dioxide. It is 1 astronomical unit from the sun. Like I said, we actually made the astronomical unit based off of the distance from the Earth to the sun, and it takes about 8.3 minutes for light to reach the sun, the Earth from the sun. And this photo is actually the Apollo 8's on Christmas Eve. The Apollo 8 orbited the moon and took this beautiful, beautiful photo, and it's my favorite photo of the Earth. All right, now we move on to Mars, which is the last of the inner planets, the ones that are rocky and didn't become gas giants. Mars has 2 small moons, which are captured asteroids. 1 Mars day is almost exactly 1 Earth day. It's 1 Earth day in 40 minutes, which actually means that the people who observe Mars from NASA follow a Mars day. So every single day, their shift gets moved back by about 40 minutes, which is why everybody who works on the Mars rotation only works for like 2 months at a time on the Mars rotation, because it really messes with your day-night cycle. 1 Mars year is 687 Earth days, and it is about 1.5 times the distance from the sun as the Earth is. It's 1.5 AUs. It has a very thin atmosphere that has a lot of oxygen in it, which is the reason why Mars turns red. It oxidizes all of the iron. It has very weak magnetic poles, which makes it harder for it to hold an atmosphere. And we know for a fact that there is water below the surface in some places, but we don't have a whole lot of data about Mars itself. We've only had probes there for about 20 years now, and they're not, they're collecting data, but they're limited by the technology that was, that they were made with. We just recently landed a helicopter, which is giving us all kinds of information, including sound on Mars, which I think is very cool. Next, you get Jupiter, which is a gas giant. It is 5.2 astronomical units from the sun. It is 42 light minutes from the sun, so it takes 42 minutes for light to reach it. It is more than twice the size of every other planet combined. It rotates once every 10 hours, which is incredibly fast, but it takes 12 years for it to orbit, and it has over 75 moons. But we know very little about the planet itself, other than it's filled with gas. Like, we don't really know much beyond the surface level. Saturn is 9.5 AUs. It takes 83 minutes for light to reach it. It has 62 known moons. It has an unknown orbit length, so we don't know how long it takes to spin. It has a 29-year orbit around the sun, and it has hexagonal poles, which is very weird. Uranus, which is the first planet discovered by telescope. This is actually an X-ray photo of Uranus, not a real photo. We have no good photos of Uranus. It was discovered in 1781, as I mentioned. It actually sits at an almost 90-degree tilt. And it has 27 known moons, all named after literary figures, most of them from Shakespeare, which I think is pretty fun. And we know almost nothing about it. Neptune is even less known, but it has better photos. It takes 165 years for it to orbit around the sun. It was discovered in 1846, but it was predicted in 1843. It has at least 14 moons that we know of, and it is sometimes further out than Pluto. Sometimes Pluto has sort of a wonky orbit and gets in between it and the sun. It is 30 astronomical units, so it is 30 times the distance that Earth is from the sun, and it takes 249 minutes for light from the sun to reach it. And then finally, on the outskirts, you have what's known as the Kuiper Belt, which is this belt of debris around the solar system, which ranges from 40 astronomical units to 100. Pluto and some other dwarf planets live out there, and we know almost nothing about it, other than it's just got a lot of debris in it. The further out you go, the less we know, which is kind of an interesting thought. So some challenges to our knowledge include we don't know how long it takes for, the problem is these planets, especially the ones out past the asteroid belt, are just it takes so long to get there that we just don't know. It requires a lot of forward planning, and we just don't do that very often as a society. Sit down and say, we're going to do this in 30 years time. There's not much incentive beyond scientific knowledge, which I value highly, and a lot of people value highly, but it doesn't pay the bills. Scientific knowledge doesn't always pay the bills. So a huge issue behind us exploring further is scientific knowledge. And also, it can be very expensive. At least that's what they tell you. In reality, it's not that expensive in the grand scheme of things when you look at other forms of government spending, but that's the argument that I hear a lot. So I've got a few additional resources, and if you care for more additional resources, you can always email me, but I have them pulled up here. So this is theplanetstoday.com. It shows you where the planets are in relation to all the other planets, and also the lunar phase. We're at a very, very small crescent here, but you've got the Earth and the Moon, and Mercury is almost behind the Sun. We cannot see Venus because it is behind the Sun right now. But things like Mars are clearly visible in the night sky. Saturn is pretty close to the horizon. Same with Jupiter. Things like that. There's also the geocentric view, which if it will load here we go. It shows that like I mentioned, Venus is going to be almost directly behind the Sun, so it's not going to be easy to spot, but things like Saturn and Jupiter, which are kind of low to the horizon, Mars is going to be on the opposite side. Those are all things that you can spot. It also shows you where some of the astrological constellations are going to be in the night sky. Some other things are, here's NASA's website on some of the missions that are currently being undergone and are in the works. So if you ever want to learn about what sort of projects there are, that NASA is trying to do. These are the things that we're moving towards, and there's a ton of them on here. Um, this is a website. It's called timeanddate.com, and it tells you in a slightly different way where things are going to be in the night sky at any given time. So Jupiter right now is below the horizon, but if we move it, say, forward a little ways, let's see, is Jupiter ever going to come up above the horizon? There it is at about 5:30 in the morning tomorrow. Jupiter's going to rise through the night sky, which is a pretty good thing to know, I guess. And it's going to rise in the southeast. And you can do that for all the planets on here. You can really look for any celestial body using this website, which is a pretty good website. It is called Time and Date Astronomy/Night is the one that I'm on. And then also the tried and true, NASA has a whole bunch of information on the planets just on their website. This one's solarsystem.nasa.gov, and it's got a whole bunch of information there. And of course, you can also always email me at eritnour@chiha.org if you ever have questions or are looking for resources. I can try to find you some as well. Well, that is my deep dive into the solar system. I hope you enjoyed it, and I thank you for coming.